Okay, Bismillah ar-Rahman ar-Rahim, salatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. So today's lecture is about machine translation, which is one of the hottest topic in linguistics and in machine learning since long time ago. And it's not surprising that the seminal paper about transformer was applied to machine translation. And that was a big milestone in the whole machine learning and deep learning ecosystem. And in this lecture, we're going to go through the history and the evolution of machine translation since it started maybe in the 50s with rule-based systems until we reach what we call right now neural transformer. Okay. So machine translation is basically about converting a text from one language, from one natural language to another. And it started a long time ago, since the 40s, and was inspired by Warren Weaver in 1949, where he started to put machine translation as a potential research area. And started from a simple approach, which is based on rule-based. Basically, in the beginning was just word-to-word mapping. And it started in some very small context, but then it has made several evolutions, going from basic rule-based and handcrafted rules by humans. Then it went to statistical approaches until it reaches the neural approaches, neural machine translation. So the objective of this lecture is provide an historical context and also technical insights about these different technologies that were used in machine translations. So that will be the overview of the lecture. We're going to start with presenting rule-based machine translation, providing a historical context and also technical approaches to achieve rule-based methods. Then, from static rules to probabilistic rules, using statistical machine translation, where probabilistic models were applied, and also word alignments. And with the evolution of neural network, it was used as an extension or as an expansion of statistical machine learning models. Okay, instead of just using Bayes' theorem in natural way, so we use neural network in order to train models, and started with recurrent neural network, LSTM, and GRU. And finally, until we reach at the pre-trained transformer models that made the complete revolution on machine translation and also different downstream tasks. And finally, we'll talk about evaluation metrics. How do we evaluate the outcome of a translation machine? So the evolution of machine translation started from back into the 50s and the 60s with an early vision of Warren Weaver, influential 1949 memorandum, which proposed to treat translation as cryptography in the beginning. And there was an experiment of Georgetown in IBM experiment to try to translate the Russian language into English language by taking a small vocabulary, I think 250 words, and they used kind of rule-based mapping between the different words. But we know that making a mapping word to word, you can get the overall meaning, but semantically and from grammatical perspective is not going to be correct. And at that time, there was not like very sophisticated computing power, nor very large data sets. So all the work trying to improve static rule-based methods in order to incorporate linguistic approaches into this machine translation. Okay, so we try not only to make a word-to-word translation, but we try also to take into account the characteristic of each language on how words should be organized, placed. Okay, مثلا ترتيب الكلمات العربية يختلف على ترتيبها مثلا في اللغة الإنجليزية أو لغات أخرى. Okay, so there are different approaches like direct rule-based approach, which is a word-to-word translation, transfer, which try to take source language, transform it into a certain linguistic model, and then make the translation into the target language. And all these rules were handcrafted dictionaries and incorporating also static grammar rules. So with the evolution of computing power, there was also a period of silence between the 70s, or let's say the 80s and the 90s. It's because at some point in time there was a report that tells that rule-based approach are kind of not very relevant, and they will not have sufficient performance. So people slowed down to do research, because from the 50s to the 70s, the research, there was a lot of fun to do machine translation, especially it has also to do with military requirements and need. And then from the 80s to the 90s, the research has slowed down until later on statistical methods allowed to do machine translation without needing to make manual handcrafting of grammatical rules. And we know that in probability and statistics, we have large corpus it's possible to extract patterns, okay? And we extract patterns not using like very sophisticated feature extractions, but we are going to make like using the Bayes theorem, try to extract relationship between words into a large corpus. Okay, for example, if I have this word in this context, how often is going to appear into a similar context? So it's kind of counting approaches, and we convert count into conditional probabilities. If I have this word, what is the probability that the next word will be this one? So it's like also predicting the next word. It's kind of the initial version of generative translation methods, but it didn't use like neural network or advanced feature extractions like we know nowadays, either using RNN-like techniques or transformer-based techniques. It was based on statistical method like Markov chain modeling or the Bayes theorem, Bayesian networks, trying to find patterns and identifying relationships between different words or also phrases. And statistical methods have evolved from word-based prediction into phrase-based prediction. So instead of, for example, try to infer the next word, I will take phrases which could be composed of 2 or 3 words together. And this was proven to improve the efficiency of statistical methods. And from that time, we have seen the initial machine translation, like Google Translator. You remember in the beginning, it was not that powerful. It can do some work, but still you cannot rely 100% of it because it's not able to capture all the semantic relationships and the morphological structures of the languages, because these statistical methods are based on counting over large corpus. So we're not really extracting very sophisticated linguistic patterns. And then with the evolution of neural network back in 2012, computer vision was also explored into natural language processing. And there are some key innovations that have used sequence-to-sequence models using RNN techniques and also encoder-decoder architecture. And encoder-decoder architecture, this is like the same architecture that was used in Transformer is All You Need, but the difference in the terms of the feature extractor. So here the feature extraction was made using RNN and LSTM techniques, and they used encoder and decoder for cross-attention to map the source language into the target language. So this was proven to be working fine using some kind of attention mechanism, not self-attention that we use in Transformer, but other type of attention that have like cross-attention between the encoder and the decoder to find the relationship between the source language and the target language. And finally, until the seminal paper of Transformer is All You Need. So Transformer refers to using machine translation as an encoder-decoder architecture also. And it's based on pre-training self-attention modules for feature extraction. And it was proven to provide much better performance as compared to previous techniques. So this is just the evolution of machine translation since the start. Okay. So these are just some illustrative examples. So the early version code of Warren Wagner, he said, when I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols. So this means that there are some patterns between the languages, okay? And it's a matter of trying to decode the tokens or the words or what you call the symbols. I will now proceed to the decode. And this is like the start of the inspiration of machine translation. And then rule-based, as already mentioned, it's based on direct transfer and interlingua methods. And the idea is basically, look, either we can make word-to-word mapping, which is the simplest, or for example, you have an input. So you try to make a parsing between the input. For example, you identify the nouns, the pronouns, the verbs. So we try to identify a certain structure. Then you will find the structure of the target language, and then you try to infer the target words of the target language. But this was proven to be limited. It was working pretty much fine into very small context, but it's not scalable because the relation between the different languages is pretty much complex that we cannot control it with very simple rule-based patterns. So statistical method, they rather than relying on handcrafted rules, they leveraged large parallel corpora. So you have a corpora in the source language, let's say English, and the corpora into the target language, like for example German. And they try to learn the translation patterns automatically from the data. So in this case, we get rid of the manual and heavy human crafting of the grammar and the linguistic rules. So here we try to maximize the probability that a word, okay, the word of the translation word given a certain context. And this context can be either a word in the source language or a phrase in the source language, depending on the approach. And the aim is to find the most probable English sentence E given a foreign sentence F. So this is kind of language modeling using statistical approaches. And this is based on the Bayes theorem. So neural machine translation was very popular since the emergence or the booming of neural networks. And it replaced the complex pipeline of statistical machine translation with an end-to-end neural networks. Okay, and that could learn mapping between languages, directly producing more fluent translation. And techniques like sequence-to-sequence encoder-decoder architecture with attention mechanisms were proposed. And this is very familiar for you. It's basically the same encoder-decoder approaches that we have been learning during the course. You have an input, you create an embedding, you will make an encoder, and the encoder is going to create a feature map in the latent space, and then you teach a decoder how to take the latent space into something meaningful for human. So we will decode it from a feature map into tokens or words. And the feature extractor is used through CNN, RNN, and later on was used transformer using the self-attention approaches. And finally, we have machine translation using transformer approach, which just changed RNN with self-attention. And instead of having sequential model, we're going to have fixed context size as the input. Okay, and using the self-attention techniques, we can extract the linguistic patterns, the hidden linguistic patterns, through the multi-head self-attention module. Okay, so and this consisted in creating pre-trained paradigms and fine-tuning paradigms, as we already introduced several times, and the integration of large language model at subsequent step. Does this make sense? Okay. Of course, there are several challenges related to machine translation, like any other downstream tasks. So the low resource languages. So thousands of languages have insufficient parallel data for high quality machine translation. And there has been a lot of research that focus on transfer learning, data augmentation, and unsupervised methods. And this is why the quality of translation, for example, if you remember before, if you translate from English to French or English to other languages, it's better than translated from English to Arabic, because the Arabic corpus was not, doesn't have a lot of data at that time. But now, alhamdulillah, with the evolution of large language model, we're seeing more and more efforts towards the Arabic language data sets. Document level context. So most systems translate sentences independently, which miss cross sentence context needed for cohesion, coherence, resolution, and discourse. And that was solved by self-attention and cross-attention in transformer-based machine translation methods. Other challenges are related to cultural nuances, because the way on how to express, for example, idioms, humors, politeness level can be dramatically different from one language to another, which is very difficult to capture. Now there are many efforts in collecting data sets, and in one of the collaborations that we've made with some colleagues in British Columbia and Mohammed bin Zayed, with a lot of people from the Arabic worlds, they collected a very large data set from African context and Arabic context, okay, that can help training better large language model, including machine translation. And in order to be able to capture these nuances, we need to have a huge data sets and peer-to-peer data set across different languages. And evaluation complexity also. So evaluation metrics, there are several metrics. And these metrics, for me, they are not quite sufficient to tell you about the real accuracy. And this is why the human evaluation remains the best, but still it's very expensive. So we're going to see some metrics like the blue score, the root score. Have you heard about this before? These metrics? No? Okay, they are able to capture some kind of quality metrics, but you will see they may fail, dramatically in capturing the real quality of translation. And this is why human evaluation remains essential but still expensive. But it's often necessary for critical applications. Okay, let's dive now into rule-based machine translation. As already mentioned, so the historical milestone, I already mentioned this. And just, in 1954, the Georgetown IBM experiment successfully translated 60 Russian sentences to English using just 6 grammar rules and 250 words. So that was maybe the first successful translation between two languages. But here, the corpus is very small. And there were only 6 human handcrafted grammar rules. It was fine for a certain context, but it cannot be generalized. I mean, if you change the language or if you change the context of a vocabulary, that is going to fail. But this was like a triggering point. We can do this. Of course, there has been several improvements of rule-based translations, going from direct translation, which is word-to-word mapping. So here, what do you have? You have a source text and you have a dictionary. If you have this word, this is the counterpart in the other language. Okay, at small scale it can work, at small context it can work, but it's not efficient. Word-to-word replacement with minimal syntactic rearrangement. Only a few rules could be used in order to make rearrangement, which is the simplest approach that works directly between the source and the target language. And then subsequently, they made more improvement using the transfer-based approaches, which uses intermediate representation of linguistic structures to analyze source text, transfer it to the target language structure, and then generate the output. Because the way on how you make a sentence in a language, it's different from the other language. So what they say, let's see what is the pattern of a sentence into English. And then let's see the pattern of a sentence into Russian, for example, or another language. Instead of making word-to-word mapping, let's first try to identify the target pattern language, and then we're going to infer the words according to the pattern. So this helps to maintain some kind of linguistic structure to some extent before generating the input. And the last technique, which is an extension of transfer-based, is the interlingua-based method, which uses language neutral meaning representation. So what was the issue here? In the transfer-based, for every pair of languages, you need to make a static mapping of the structure. Okay? So this is not scalable because you need to make a lot of efforts to capture any kind of mapping between two different languages. So here researchers say, okay, why not try to find kind of a universal language neutral representation that can help to make any two languages. Of course, that was very ambitious, but it was very complex because it's really difficult to find a universal representation. Imagine that you want to translate between, any language to any other language. It's almost impossible to find static rules based on this. So that was the evolution until at some point in time when the researchers have explored any kind of situation in rule-based machine translation, there was a critic reports that say, rule-based are not efficient. And this, as I mentioned, it has slowed down a little bit the research around machine translation. So these are a few examples on how we can do this. Look now, for example, in direct translation, you have a source, dictionary lookup, and local reordering to get the target text. For example, English to Spanish, if we say the boy eats the red apple, this is a word-to-word conversion between this sentence and the following one. But in Spanish, it turns out that this structure is not the same as in English. We need to make reordering, okay? For example, here, instead of saying El Chico Cam La Roja, I think it's red, and this one is apple. So we need to make it in different way. مثل ما نقول احنا التفاحة الحمراء. By the way, الإسبانية قريبة جدا من العربية حتى في تراكيبها حتى البرتغالية. And I lived in Portugal and they have a lot of words very close to Arabic, even in the way how we pronounce it. Yeah, we can see the effect of the Arabic and Islamic يعني الحضارة الإسلامية في ذاك الوقت. يعني still it impacted the language of Spanish and Portuguese. And they are good people, by the way. They are good people, I mean, yeah. I feel like I'm in Tunisia when I'm in Portugal. Yeah, so very close. So the limitation is lacks deeper linguistic analysis needed for complex sentences. So this has limitation, it can solve some kind of simple patterns, but it cannot solve complex patterns. And in direct translation, that's another one, okay, in French. Okay, so we cannot say, even in French, we don't say rouge fleur, we say fleur rouge. So we need to make some kind of rewarding. هذا باللغة العربية. Maybe this is more easier to understand. Okay, the student reads the book. الطالب يقرأ الكتاب. Now, probably here, it just come into the right order. And we have like verb, subject, object. Preference and rich morphology in Arabic. Okay, so transfer-based approach. So try to identify more complex patterns between different languages. And this is the most widely implemented rule-based machine translation architecture with 3 distinct phases. So between the source text and the target text, so we make an analysis we need to infer the source structure, and then we need to transfer the source structure into the target structure. And this comes, you need to make static rules that helps you. If I have this structure in English, this is the corresponding structure in Arabic or in French or in another language. For example, here, if we apply English to Japanese, okay, the cat chased the mouse. Okay, so the structure here, we have a subject, we have verb, and we have an object, SVO. Now the transfer rule is that in Japanese they have a different rule on how to express. It's SOV, subject, object, and verb. Okay, so here there are some rules that can be devised in order to make the mapping between the pattern in English and the pattern that it has to be in Arabic. So having a source text, we need to first identify the structure. From the structure, we convert to the target structure, and then we will make the mapping of the words according to the structure. So here, it's better than the direct approach, which is just word-to-word mapping, because we can conserve and maintain better structure differences between the languages. But of course, it has limitation because it will miss a lot of the morphological aspects, okay, of the languages. But it can maintain kind of acceptable performance of the linguistic structure. Okay, here are some examples. For example, translating from English to French. So we have an input text in English. The small black cat sleeps on the table. And this is the English structure. So this is an article. This is an adjective. This is another adjective. This is a noun, verb, preposition, article, and noun. So now to transfer this in English structure, we have article, noun, and then the adjective. This is the way on how the expression in French are made. So first of all, we need to translate this structure into this structure, and then we're going to take the words from the mapping between both. And now look, the correspond at this word. Now here we have small, which is this one. Okay, and now we have so according to this structure, we're going to put this noun cat before the adjective. Okay, and so on. Now, with the correct translation, we need to put hadi petit, which is a small, chat noir, which means the small cat black. This is the way how we say it in French. More. Le petit chat noir dort sur la table. Yeah. So in principle, it should be article, adjective, noun, and then adjective. That could be correct for some context. I don't see, this is why sometimes it's difficult to find a universal translation between different structures. And this is one of the limitations of the rule-based approaches, is that at some point in time, these rules becomes very complex, conflicting, and confusing. Okay, especially when you want to scale into the context. So same thing here. We can try to make a mapping between English structure, Arabic structure, which is completely different. Okay, look here, it starts with two smart girls. So this is encoded as Bintan. Okay, wrote, katabat. So it's pretty much different. Look now, we start with a number, adjective, and noun. And the Arabic structure starts with a verb, then the noun, then the adjective. Okay, and probably this works in this context, but we don't know whether this could be universal or not. Of course, now at this point in time, there is a need of a huge expertise of linguistic scholars to be able to derive these rules. I mean, only computer scientists, they cannot infer this rule. So this is why it was a very interdisciplinary approach. But now with transformers, we don't care about these linguistic patterns because they are going to be automatically inferred during the training phase using the self-attention. So now maybe you can do more linguistic research in AI. I don't say without having to have full recourse to linguistic scholars, but with less reliance of linguistic scholars. Of course, we need to have linguistic scholars to validate the output of the machine translation. But with rule-based, these type of rules, you need to have very deep expertise, because this is like the difference between machine learning and deep learning. What is the difference between machine learning and deep learning? Yeah, in machine learning, features are handcrafted. Okay, so now it's like we are extracting features by humans, and then we don't even do training here, just to do one-to-one mapping between the words. And now with statistical learning, we have less reliance on handcrafted features. So features are discovered using the Bayes theorem, and then they were discovered using the neural network learning. Okay, this how was the evolution. And with the transformer, the good thing is that we can have much better understanding about the relationships in a global context. Okay, so interlingual approach is the most ambitious architecture which try to use language independent semantic representation. So we try not to have like language to language mapping, structure mapping, but universal mapping between languages. So that was kind of a very ambitious, but it was creating truly language independent representation is extremely difficult to achieve. Okay. And this is an example. If you want to translate from English to French, so we will have an input text. She will arrive tomorrow morning. And then the interlingual representation, let's say that this, we try to infer what is the action, what is the agent, what is the time, the tense, the aspect. And then based on this, it can be translated to different languages. Okay? Because this, let's say this universal mapping, everyone will have a corresponding mapping to a certain language. So this is why we said here, if we have n languages, we're not going to have n square pairs, like in the previous context. In the previous context, if you have n languages, you will have n square combinations of the mapping between the rules. Here we have only n combinations. So you have a static rule, and then for each language, you're going to find its corresponding parsing technique, okay, to convert it to the target language. So there are strengths and limitations of rule-based machine learning analysis. So the strength of rule-based approaches, they have predictable outputs because the rules are handcrafted. Translation are consistent and predictable. So it's kind of a static translation. If you make the translation thousands of times, you're going to find the same result, all these iterations. There is no training data required. Okay, can be built for language pair with limited parallel text. There is a linguistic control. Okay, linguistic can directly fix specific translation problems. And it has the benefit of domain adaptation. The rules can be tailored to specific domains, legal, medical, etc. However, it has a lot of limitations, of course. So this is labor-intensive development because it's based on human-crafted rules. So creating comprehensive rules sets requires years of works by skilled linguistics, and this is why I mentioned that there is a big reliance on linguistic experts for rule-based approaches. And there could be also rule conflicts. So as rule sets grows, the interaction between the rules becomes increasingly complex and also unpredictable. There could be a coverage problem in the way that it's impossible to cover all the linguistic phenomena with explicit rules to translate between any language to any other language. So there's going to be always issues, okay, especially if you go to a broader context. And this is why these rule-based machine translation techniques are still popular right now into very context-specific applications. Why? Because they are not resource intensive and they can actually provide you very quick results, but in very small context. Okay, and I'm going to show you a few examples. And the maintenance complexity, adding new rules or vocabulary often requires diverting the existing rules to avoid conflicting rules. And look at this example. For example, time flies like an arrow. Now, using rule-based, this can be confusing to establish a correct rules. Why? Because it can have three interpretations. So we can read it as time flies as the passage of time. It means move quickly. Time flies like an arrow. It means the time move very quickly. That's a possible interpretation. Another interpretation, there is a type of fly, it's called time flies. Okay? And here it could be interpreted as enjoy an arrow. Like is enjoy. And the third interpretation is the measure of the speed of flies. Time flies the same way you would for an arrow. Okay, so you can see with rule-based we could have some ambiguity into extracting the structure of a certain sentence. Okay, these are some popular real-world rule-based machine translation systems. We have Cistran from the 70s. Okay, it was used by the US Air Force. So in the beginning, it was triggered as a military application, and then by the European Commission to translate between European languages. And also, this was used by the early Google Translate. And this is why it was kind of, I don't know if you have the experience to use Google Translator 15 years ago or maybe 20 years ago. It does some job, but still, just for you to understand the basics of the translation, but not something to rely on.
It wasn't able to translate like a full sentence.
Yes, because the problem was, these rules can solve a problem, but they cannot capture the complex relationship of a language. Had the transformer, why it was a miracle? Because it solved almost all the problems of the past 70 years of research. Okay, so we had to wait 70 years of research until to be able to find a way to model the language. This is why we call it language modeling. And I have been hearing about machine translation, NLP at that time, but these results, when you see the applications, were very limited. The booming started with maybe the AlexNet era in 2012, when we see neural network are able really to capture complex patterns, and with recurrent neural network in NLP, and it only lasted 6 years to get transformer up and running, and then things have completely changed since that time. Okay, so now probably we focus less on capturing relationship, but what we can do on top of these models as applications, as sophisticated applications. Okay, so there is also Meteo, which is disconnected. It was operational from the 77 to 2001 to make translation of Environment Canada between French and English. Canada, it has bilingual country, so they were able to have rule-based approach to make automatic translation. So you can see that in this kind of simple context, rule-based approaches could be efficient. Could be reliable because you have a small vocabulary, and you can easily make the translation by extracting simple rules and translating from 2 languages in this case. Okay, it's processed using 30,000 words daily for 25 years. And it has over 99% of translation required no editing. And this is another one which was used from 2004 to present, used for related languages, website localization, and it's open source. And it's used especially for languages that are close to each other. Okay, it has shallow transfer approach for related languages, like for example, Czech and Slovak, Spanish and Catalan. These are very close languages. Okay, so it turns out that rule-based approach was like the triggering point for machine translation, but they were limited to provide something like sophisticated translations. And statistical machine translation was like the second solution that has boomed from the 80s to the 90s. And the core idea is to learn translation from parallel corpora. You bring corpora in English, another corpora, for example, in Arabic, and then you try to learn the likelihood of a word to appear under a certain context, given a certain context. So it's based on conditional probability. Okay, for example, if I have this sentence in English, what is the probability that this word will appear, or this sentence will appear in Arabic or in French or in the target language? So it's a counting-based approach. Okay, and you know that we can have a good statistical convergence over a large corpus analysis, and this is based on the central limit theorem and the law of large numbers, that if you process large amount of data, you're going to have a convergence to a statistical mean. And the optimization technique to learn is based on expected maximization learning approach. So the probabilistic inference maximizes the likelihood that the target given a source, conditional probability. And there is a pioneer work from Brown and co-authors in 1993. And IBM was leading actually this topic. They provided different models from model 1 to model 5, which I'm going to explain. Okay, so this is the evolution of statistical machine translation. Manual rules and dictionary dominated by, this is what we have been talking about. And then we had IBM model from 1988 to 1993. So Brown and co-authors introduced the first generation of the word-based statistical methods, which pioneered the use of word alignment and probabilistic translation. So in the beginning, they were relying on words, but it turns out that the condition probability of a word given another word could be improved if we consider a phrase given another phrase. لأنه غالبا phrases, the mapping between phrases, it can maintain some kind of semantic relationship and structural relationship much better than word-to-word frequency. For example, instead of having the translation of a house given مثلا for example بيت ولا منزل, ممكن مثلا عندك المنزل الصغير, okay, given you have the small house. Instead of having small with صغير, منزل with house, so we're going to take chunks of words all together, and this is what we call the phrase-based, and started to work in 2003. So they Cohen extended the approach to translate phrases or word sequences rather than individual words, dramatically improving the translation quality. And you know, here they just increase the context. The contextual representation of the information is better captured in a phrase rather than individual words. And then we have advanced statistical machine translation from 2005 until 2015 using hierarchical phrased models, syntax-based approach, and improved decoding algorithms to enhance SMT until neural machine translation have emerged. So the core idea is based on the bias theorem, okay? Probability of A given B. But what is A, what is B? You know, here, here we try to infer the target language given the foreign language. The probability of the English word given the foreign word. And you know, what is this probability of the foreign word given the English word? This model how words in one language map to words in another language and learned from parallel corpora. And PE is actually the language model. The language, if I take English sentence, you know, there is a statistical distribution of words within the whole English corpora. So you can know what is the probability of the word the appearing in a sentence. What is the probability of the word car? And this is what we call the language model. It was captured by a probability distribution. How we make the probability distribution? Very simple. Take a corpus, calculate the number of words, divide by the total number of words, and then you will have kind of histograms. Okay, and this can be approximated to a certain probability distribution. And this was used in security, okay, to infer the distribution of words, to try to infer scrabbled sentences. كانت من أحد السكيورتي اللي كانوا يعملوها فيها من قبل إنه they flip the words ولا they flip the characters. مثلا عندي كاركتر A نغير الانكودينج حقه نزيده 3 ولا شيء يتغير. لكن using statistical approaches we were able to reverse it. لأنه حتى الليترز في كل language عندها distribution معينة. So that was not a very secure approach. So statistical approaches were used in a way to decode some of the early cipher codes in security inside the language. Okay, and this is data driven. So you don't need any explicit rules. You don't need to make any manual work here. But of course, this comes at the cost of having a large amount of data. Otherwise, you will not have statistical significance. And all translation knowledge is extracted from parallel text. Okay, so how SMT works, as a simple example, this is a Spanish sentence and this is the English sentence. So the translation model, they learn the word or phrase mappings. Okay, for example, the probability to have casa given house and the probability to have blanca, it's given white. So it's like, you can think about like a softmax function given a word. You will have like a softmax function saying for this word, the highest probability or the most likelihood word is this one. So you'll have kind of probability distribution of a word given a certain word. This condition probability is going to change given the context. Okay, it will change given the context. And this one is not going. This is like the language model. It's kind of static distribution. Okay, and we have the language model. It learns English fluency. The White House is more likely than the house white. Okay, so it's able to learn the structure of the words within certain language. And the decoder, it searches the sentence that maximizes both translation and language model scores. So let's start by word-based models. The first generation of statistical models worked at word level, and the IBM researcher developed a series of increasingly complex models from 1 to 5 to establish the concept of word alignment, mapping between words in a source and target sequence. And this influential model introduced by Brown, so we already mentioned this. Okay, so let's start with the first. I think I have a code that shows this. Just let me check it. I made a code. I will try to find it. I have a code that shows how the statistical model works. Okay, so this is the core concept as already explained. And then IBM made different models. So the idea is to learn word translation from probabilities, or the word translation probabilities. So here we have English, the black cat, and the Spanish, this is the translation. And the algorithm is basically based on counting, okay? For example, for the English word, the probability of having L given V, okay, is going to be to give you a certain value. And this is based by making a complete statistical analysis of these two parallel corpuses. Okay, so we will have for every pair of words a probability. And this will give you the maximum likelihood to find the target word given the source word. And this probability would be then determine the most likely words alignment in the new sentence. Okay, so it's basically, let's say, it's kind of a frequency-based approach as an alternative to neural learning, because the same way also is going to be learned by neural network. But in this way, since we don't have neural network learning, so they're going to learn by analyzing the frequency of occurrences of the words altogether. And this is the first IBM model, which is the simplest one. Okay, it's based on calculating the frequencies of the words and try to make the word alignment between them. So for example, here in Japanese, they don't have any word that corresponds to it. They don't have it. So this word will be not aligned and will correspond to a null value. So null, it means that for a certain word, there is no corresponding word in the target language. And will also, it's not aligned in Japanese language. And then we will have alignment, for example, this corresponds to tomorrow, and this corresponds to surely, and this, the alignment of word is going to change, and this is going to be learned through the frequency-based approach, okay? And the IBM progression went through different models, model 1, model 2, which adds the alignment probability. So this base, it's only uniform alignment probability. And the model 2, it adds another information to this probability model to also learn the alignment probability based on the position of a word in the target language. And then other techniques added fertility, then improved the word ordering, and finally the model 5 fixed deficiencies to ensure valid alignments. Okay, so the IBM model was successful, but still they were not able to capture all the nuances into the linguistic patterns from the source language into the target language. So a substantial improvement was used phrase-based approach in statistical machine translation back in 2003. And the phrases are just contiguous word sequences. Instead of having condition probability or word given another word, we're going to make a phrase given a source phrase. Okay, and this is now the phrase table. We will have a table. At the end, it's going to converge to a table for every sentence, for every phrase, what is the probability or the most likelihood for the phrase target. And the language model is for the fluency. So the phrase is defined as a continuous sequence of words. Example, take off is treated as one unit rather than two separate words. And this was proven to significantly improve the translation quality by capturing the local context and the common expressions. So at the end, this phrase-based translation is going to result into the phrase table, which will be a dictionary for phrase pairs with their translation probability, okay, using statistical analysis. And this extracted from word-aligned parallel text. So different models were proposed just try to improve the alignment probability given a certain context between any two languages, okay, to make the translation appears like natural in the best way. Okay, they were kind of successful, but still not sufficient for more complex patterns. Okay, Bismillah ar-Rahman ar-Rahim. Salatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. So in the previous lecture, we talked about the initial approaches for machine translation, and initially it was based on static human handcrafted rule-based techniques, and these approaches started from the 40s up to, let's say, end of the 90s. And these approaches, the rule-based approach, were very limited because they cannot capture all the nuances between two languages, the source language and the target language. So one major improvement is to use statistical-based approach or statistical machine translation in order to infer the patterns between two languages using statistical approach based on the bias theorem and the frequency between the two corpuses, either based on words or based on a sequence of words that we call phrases. And the next evolution of machine translation is based on neural networks, and starting from 2014, 2 years after AlexNet and computer vision emergence with deep neural networks, where computer vision have used convolutional neural networks, and in natural language processing, RNN, which is more tailored for sequential models, was actually booming at that time and was applied to machine translation, speech recognition, and different downstream tasks. Okay, so this is basically going kind of a review of neural network and recurrent neural network for sequential modeling. So neural machine translation is an end-to-end approach to machine translation that uses neural networks to directly model the mapping between the source and the target text. Instead of making manual feature extraction, we're going to use neural network for automated feature extraction using recurrent neural network system. So the neural network systems, they learn to translate directly from parallel data. So given a certain sentence, what is the probability of a sentence composed by tokens from Y1 to YT given an original sentence between X1 and XS? And observe here that the number of words into one language could be different from the number of words because you can translate any word, a sentence with different number of words into the target language. And this conditional probability is equal to the sum of all, of YT given the previous, the original sentence or the initial language sentence and the tokens from Y1 until YT minus 1. So what is this? It's the previous context. So this is like text generation based on the previous context. What is the previous context here? The full sentence in the original language and the generated sentence, the partially generated sentence in the target language. Is this clear? Okay. So this is how it works. So we will have here end-to-end learning. We don't need to infer rules. We don't need to make prior statistical inference. Okay, so a single model, it will learn to translate directly from examples. So when we train a model, we're going to put the whole sequence, initial language and the target language all together, and the recurrent neural network is going to learn from that sequence, okay, on how to generate, let's say, the next token. This is like next token generation. And neural network, it will leverage deep learning innovations or representation or feature extraction like the RNN, LSTM, GRU, and transformers later on by using self-attention on a fixed context window length to model the complex language patterns. Of course, this has emerged from distributed representations, the embedding that we talked about before. Words and sentences are represented into dense vectors in a continuous space to capture the semantic similarities and semantic relationship. And attention modules were introduced to allow the model to focus on different parts of the source sentence when generating each target words. So here, RNN, LSTM were used as a feature extractors, and encoder-decoder architecture was used to actually make a cross attention or relationship between the source language and the target language. Okay, so how it works here, we're going to start from a source language sentence, for example, an English language, and the target language, for example, French. And you will have an encoder. This encoder is going to convert the source sentence into a sequence of hidden states, and it's the latent space, the feature extraction. Okay, and you will have an attention module that will connect the encoder to the decoder. Okay, هذا نفس الفكرة بتاع attention is all you need. كل الاختلاف كامل موجود أين؟ في طريقة الفيتشر extraction. وهذا encoder decoder in this case, it was used before. Okay, allow the decoder to focus on relevant source words at each step. And finally, the decoder is going to generate the target sequence or the target sentence one word at a time. Okay, هذه الفكرة هي بداية language modeling. Okay, making it so generating the text, the next token based on the previous context. And each word is predicted based on all previous words and the attended source text. هذه فكرة الانكودر decoder. What does the encoder do? What does it do? It takes a sentence, it results in what? Feature vector, okay? And from this feature vector, which is the latent space representation of the input, is going to do a cross attention with also a feature representation of the output, and then it's going to help generating what will be the next token based on this whole sentence, this sequence. اوكي هذا كله it will be translated to a feature vector اللي هو cross attention ما بين source space and the target space, and this will help generating the next token. Okay, so this is how we can understand this equation. Okay, it's not complicated with all the background that you know so far. Of course, different ways on how to extract features using recurrent neural network or different other variations. So the encoder will process the source sentence using RNN, and you should be familiar with this transformation. Okay, we use tan-H, nonlinear transformation between the previous state or the hidden state and the memory. And the decoder is going to take this generated feature, and finally we'll use a softmax function, train a softmax function to infer what will be the probability of the next word based on the whole context. So the encoder will process each input XS and update its hidden state HS. This is the input, this is the hidden state, and then the final hidden state becomes the context vector, which is this one, which is the feature vector. This feature vector HS, okay, will be used in the decoder to will update the hidden state based on the previous state, the previous output, which is this one, and the context vector C, okay, which we calculated from the previous state. And finally, the softmax layer will convert the hidden state to a probability distribution over the target vocabulary. Okay, so now if you understand this, you can see that the transformer architecture by itself is not an innovation. What was the innovation? It's just the self-attention module to help the feature extractor. So here the feature extractor was based on sequential modeling, and they are saying, okay, instead of doing that, let's take a fixed context size and process all in parallel. لأنه مثل ما تكلمنا في RNN, one of the drawback of this architecture is that it is sequential, so we cannot do parallel processing. ما هو مثل الترانسفورمر, we can take a big sentence ونقسموه على multiple attention head. Okay. So here there is a key innovation from source center reversal. Here in this paper they found that reversing the source sentence, for example processing I am student as student I am, significantly improved performance by creating shorter dependencies between corresponding words in a source and a target. That was one of the findings in this seminal paper. There are two seminal papers about machine translation using sequential models. And of course, for feature extraction, afterwards, they've tried different variants of RNN, LSTM, which capture the long short-term memory. We have introduced this, and GRU, which is also another version of LSTM that can learn long-term dependencies more efficiently. And these are LSTM equations that we have already introduced in the RNN lecture. Okay. And here they have used in neural machine translation the concept of attention, which is different from the concept of self-attention. So attention mechanism allow the model to focus on different parts of the source sentence when generating each target word. So it's kind of attention between the source and the target. And there are two versions of attention here. The first one is no attention, which uses a single layer to compute alignment score between the source and the target, and Luong attention, which uses two-layer feed-forward network to compute these alignments. So here I summarize the difference between attention and self-attention. Okay, so the traditional cross-attention, it uses an encoder-decoder model to allow the decoder to focus on the relevant part of the source sequence. Whereas the self-attention, as we already introduced, it tried to capture the mutual relationships between different words into a single sentence. هذا self-attention, it's the dependencies into a single sentence, and the cross-attention is the dependencies between the source and the target sentences. And they were implemented into an encoder-decoder architecture with a feature extraction using RNN, LSTM, and GRU, and in model transformer with a feature extraction using self-attention as feature extraction. Of course, we have already discussed the limitations of recurrent neural networks and its variant, and these are the same limitation in early neural machine translation, which are based on RNN and LSTM. They suffer from bottleneck, they suffer from the issue of non-parallelization because it's a sequential modeling, and also the loss of information over long sentences, even with LSTM. And this is why self-attention was proposed with transformer models, as we already introduced. Okay, and this is the original architecture of the transformer architecture for machine translation for the paper back in 2017. Attention is all you need. And here the summary of key contributions was dispensing the recurrence by providing the input altogether into a fixed sequence length. So that paper, it has used 512 tokens in the input sequence length. And they have used positional embedding using the sinusoidal function. And they have used self-attention mechanism for the first time to allow the sequence to attend all positions, capturing the long-range dependencies more efficiently. So we have an encoder, we have a decoder. The decoder will contain the target language. The encoder is going to contain the source language. So what will happen? It will go through several multi-head attention layers, and then it will calculate a feature extractor, and this also will calculate a feature extractor here. And finally, using cross attention between the source and the language features, it will be calculate the combined latent space feature extraction, and then it goes until at the end it will apply the softmax function for the generation of the next token. And the breakthrough that the transformer made is that it has achieved a score of 28 in the blue score over the English-German translation dataset. So I'm going to introduce you to this type of blue score. So these slides are just a summary of the transformer architecture that was proposed in the paper. Attention is all you need. We had already talked sufficiently about this. You know, this is the equation of the attention, the query, the key, and the value. No need to talk again about this. I think you are already familiar about self-attention right now. But just for you, and you know, the need for multi-head attention, we had a full lecture to justify the need of parallel computing. This is the positional encoding using the sine and the cosine function to capture and to embed, or to encode in this case, the position along with the embedding vector of the different tokens. Okay, so the last part of this lecture is about evaluation metrics, which is really important, so please pay attention to this part. Now imagine that you train the model that will translate a sentence from one language to another, and then you want to make sure about the performance of your translator. So the question now, how do we evaluate the performance? So, you know, for me the best thing is that it must be evaluated by a human, but this is very expensive. You know, if you're going to translate thousands of sentences, you cannot, it's possible, but still it's going to take a long time and could be also costly. Now, of course, maybe we can use a large language model to verify the translation quality, because large language model now they have human-like capabilities in also evaluating sentences. But you know, the common evaluation metrics are known as blue and rouge. Okay, so it doesn't mean blue it's the blue color or rouge is the rouge color, but it's an abbreviation of recall-oriented understudy for gisting evaluation. Okay, and this one is an abbreviation of bilingual evaluation understudy measure. And this is an abbreviation of blue and rouge. It's just by coincidence, it's like the name of two colors. So what does it mean? I'm going to provide you detailed feedback over this. So basically this is more focusing on precision. You know that in classification we have precision and recall, and I'm going to show you in details how this works. And rouge is emphasis on recall with variant of different matching types. And meteor is something that is in between. It's kind of the F1 score in machine translation evaluation metrics, like in classification. So try to balance between precision and recall with synonyms and word orders. So let me go to the detail just to see how it works. So the blue metric, it tries to measure how similar a machine translation to a reference translation. And it is always a value between 0 and 1. Let's go directly to the practice. Okay, look at this example here. Imagine that you have a reference. For example, you translate a sentence and the reference translation is the cat is sitting on the mat. This is what we expect. but the machine has generated, the cat is on the mat. Now the question, how do we evaluate this programmatically? In the blue score, so we will use as following. We're going to make n-gram matching. What does it mean? N-gram is either word by word matching, or to pair of words to pair of word matching, or you can increase the sequence in the way that you want. So let's look now, this sentence and this sentence. The cat now, the machine sentence is matching with 6 words out of 6. Although here we have an additional word, but we look only at the matching words, regardless even of the order. And this is why, it's going to give you from one perspective. I expect to have these words and I got them. So in this particular case, we have the blue score is equal to 1. But this is not sufficient because we can have order in any way. So let's try to improve this by considering bigram, every 2 words together. So here I have the cat, and the cat is, look now, I start to capture more the sequencing with the bigram, but only consecutive words together. So I have here a match is sitting here, it's not, okay, I don't have is sitting. So this is a miss. In the machine also I don't have sitting on, so it's another miss. But I have on, the, and I have the mat. So now counting, I will have 4 out of 5 machine bigrams, which makes 80% of the match. So the blue score in the bigram is 80%. We can do the same thing for trigram. And here we're going to find that we have only 1 match out of 3 machine trigrams, which makes 25%. So when we increase the number of sequential words, okay, we will have a blue score that is smaller, until at the end, if I take the 4 consecutive words, I'm going to find just a matching equal to 0. And this is going to be very penalizing. So now we need to calculate the combined score, which takes into account all of these different n-gram levels. But we will also use a brevity penalty here. And if we look now, this one, it has 7 words, and this one has 6 words. So the brevity penalty equation is equal to exponential of 1 minus 7 divided by 6, and this is going to give 0.85, almost 0.85, because this one is a little bit more brief than the other one. So we consider this with a penalty, okay, because we're expecting to have 7 words in output, but it's giving me only 6 words in the output. And the combined score, it's going to be 1 multiplied by 0.8 multiplied by 0.25 by 0.0001. Look, we replace the 0 by 0.001 to avoid zeroing the blue score. So this is going to give 0.224, and this is going to be considered as the blue score of this translation. Okay, now from human perspective, maybe this is sufficient, but the score looks like it's a little bit low. Now the blue score, I need also to multiply by this brevity penalty. So it's only 19% of blue score. It's too low, right? But it's not very bad from human perspective. So it's actually a metric maybe to compare between different machine translation algorithms or models, but it doesn't necessarily mean reflects the real quality of the translation. You see what I mean? Okay. So the advantage is fast to compute. It's language independent. It correlates with human judgment, it's not really to me. Simple to implement. However, it cannot recognize synonyms. That's one of the issues. If you change, I don't know, cat by another synonym, or something else, it's going to be a miss. Or car, vehicles, that's going to be a miss. Limited evaluation of word order. It's almost, this one doesn't capture the word order. This is a partial capturing, it's still partial capturing of the word orders. And it reads all words equally. And this is unreliable for single sentences. Now another metric is the Rouge metric, which is the recall-oriented understudy for gesting evaluation, is a metric that measures how much of the reference translation is captured in the machine translation. And it's also a score between 0 and 1. There are 2 variants, the n-gram recall and the longest common sequence recall. Let's see this in practice. let's say we have the following reference. The cat is sitting on the mat, and we have the following machine translation. On the mat, there is a cat. Now, let's calculate Rouge 1, unigram matching. So basically here we're gonna have, we have here 6 words. And how many matches we have? 5 out of 7. 1, 2, 3, 4, 5, 6, 7. And we have 5 matches because the and the is the same. So this is going to give 0.71 or 71%. Now if we make Rouge 2, we're going to make bigram matching. We have on the and the mat. On the and the mat, it's there, and it's there here also. And this makes 2 out of 6 reference bigrams. Here we have 6 bigrams in the reference. Yes, and here we have 7 reference words in the reference. So this is how we calculate the Rouge score. And for longest common sequence, we try to find the longest sequence that is the same on both, regardless of the word order. Okay, so here we have the cat on the mat. If you see in the machine, we don't have the cat on the mat altogether, but it can be, we can find here the cat on the mat in the machine. So the longest sequence that appear in both texts in the same order, and this makes 71% also. So let me explain more the Rouge L to understand it better. Now, for example, if we have the original sentence, the cat is sitting on the mat, this sequence, the cat on the mat word appear in the same order, the cat on the mat. ولكن بالرغم اللي عندي is sitting جاي في الوسط، لكن I can still read in the same order the cat on the mat. But if I remove only this part. But for example, if the original is the cat is sitting on the mat, now mat the cat, it's not a valid sequence here. So this is a valid sequence, and this one is not a valid sequence. Okay, this is just to understand that the sequence is the longest number of consecutive words حتى لو ما كانوش متصلين, even if they are not necessarily consecutive. The longest maybe non-consecutive list of words, okay, or sequence of words. So the key difference between Rouge L and Rouge N, okay, is unlike n-gram, the subsequence words don't need to be consecutive, not like Rouge N. Rouge N, they must be consecutive, and Rouge L, they should not be consecutive. So every kind of metric is able to capture certain nuances of the relationship between the translated text and the original text. Does it make sense? Okay, look at this example here. Find the longest common subsequence. Okay, so the cat on the mat. This is the longest sequence in the reference that can be made of the words from the translated machine. واضح? So why Rouge L is equal to 5? Because I can make a combination of these words that will match this sentence, okay, without is sitting. Think about it. Do you have questions? Okay. To find the long common subsequence, we look for the longest sequence of words that appear in both texts. Okay, the words the cat on the mat appear in both texts. Maintain the same relative order. In the reference, we have the cat on the mat. On the machine, we have on the mat cat. We can rearrange the order, okay, to match the reference order. So this is how it works. Now, we have already said that Rouge is focusing on the recall and blue is focusing on the precision. And Meteor score was introduced to make a balance between both evaluation metrics. So the Meteor is an abbreviation of metric for evaluation of translation with explicit ordering, and is a metric that improves on the blue by recognizing synonyms and focusing more on recall than precision. And it's always a score between 0 and 1, where 1 meets the perfect match. So the advantage is that Meteor can recognize synonym and word variations and not the exact match, وهذا يعطينا أفضل to evaluate better. Okay, لأنه أنا ك end user I can accept أنه automobile is similar to car or vehicle. However, with rouge and blue, this is not going to be accepted. Okay, so not exact matches, making it more aligned with human judgment. احنا كبشر نقبلوا synonyms مش بالضبط، لأنه when you train a model you will have a sentence and its corresponding translation, but the problem you can have multiple translation to the same sentence with different wordings. فالآن having one-to-one mapping doesn't necessarily provide a good estimation with blue and with rouge. But the combination of both with Meteor score can solve this issue and be closer to a human judgment. Okay, so this is how it works. We match word between the reference and machine translation using exact matches, stems and synonyms. Okay, we calculate the matches حتى باعتبار synonyms with stems. مثلا الآن cars and car, we consider this is a match, not a miss. طبعا يمكن from linguistic perspective يكون في خلل، لكن from meaning perspective it still make the same sense. يعني هذول كلهم approximations to the quality of translation. Okay, and then calculate precision and recall. Calculate the penalty of fragmentation penalty مثل ما عملنا من في briefty penalty, and finally calculate the final score, which is the F mean. It combines precision and recall مثل F score multiplied by 1 minus the penalty. And this is an example here how the Meteor metric works. The boy, مثلا if we have a sentence, the boy ate an apple and the lad consumed an apple. Now of course with the blue score, boy and lad ate and consumed will be considered as a miss. However here, let's see how it works. We have matched words, 5 out of 5, because I will consider all words are matched through exact or synonym matching. So I consider there is a complete match. The precision is 5 out of 5, the recall is 5 out of 5, the F mean is 1, and we have the number of chunks as shown by the underlines in the example. We have 3 chunks here. Yeah, this is the first, the second, and the third chunk. And the penalty is calculated based on the equation 0.1, and this will make a Meteor score equal to almost 90%. And this makes more sense من اللي 19% اللي شفناها في البلو score, okay, or the rouge score 71%. So as a human you can have this could align much better than with the human judgment. So in comparison, the blue score focuses on precision with exact matches only and uses the n-gram overlap with no linguistic resources. For the rouge, it focuses on the recall, the exact matches only also, and can use the longest common subsequence for word ordering with no linguistic resources. For the Meteor, it makes the balance between the precision and the recall, with more favors on the recall, and matches both synonyms and stems in addition to the exact matches, and uses chunks-based penalty. But it requires a dictionary also to have the synonyms between the words and their counterparts. So the best for machine translations to use Meteor for evaluating translation where meaning preservation is critical, even the exact wording differs. Okay, so this is for the lecture. Now I've made you this time a GitHub repository, I think it's this one, with different hands-on activities. Okay, so you have here a complete tutorial about how to get started with machine translation. Okay, so I have 4 scripts. One for basic translation. I'm going to run it right now. It's simple example with using pre-trained models. We downloaded pre-trained models from Hugging Face or NLTK, and I'm going to show you how we can use this model to translate. Another one is the translation evaluation using blue scores. The third one is about showing the model architecture of transformable based models. And fine-tuning, this is if you want to pre-train a model. If you have a data set, you can pre-train a new translation model. Or you can bring a pre-trained model, bring your data set and make fine-tuning. Okay, that's possible also to improve the quality. So let's start by basic translation here. We're going to run this script. It's a simple translation example.py. Of course, if you want to run this locally, you need to install all these dependencies. And it's preferable to have a GPU, okay? Because some of the transformer-based, they're going to require a GPU for fast execution, but still, it can work on a CPU as well. So this simple translation example, what it does, it will use transformer from Hugging Face to import the pipeline, and here it will download the pre-trained model, Helsinki NLP Opus MT between English and German, DE. So here we can provide a text in English, we call the translator, and finally we can treat the translated text as the first input, okay? Because if you provide one sentence, you're going to have one answer, but you can make batch translation. You can send several sentences and you will have several translated text, and you can access them through the index. So let me run this quickly. Basic translation, Python, simple translation.py. I'm going to take you through the code, but let's see the execution. Of course, there are many packages that have to be downloaded, and it makes translation between English and French here. Okay, so look here, it's using my GPU, which is MPS. If you have MacBook Pro, so it's going to be MPS GPU. If you have Windows, it should be NVDA. And here I have fast execution. This is example number 1. Machine translation is transforming natural language processing. And look now, this is the expected translation. And this is the translation from the machine. Okay, what is the blue score here? It's 1, because we have an exact matching between translation and the reference. Look at the second one. The quick brown fox jumps over the lazy dog. So the reference, this one, the rapid runner, okay, and the translation text is this one. Okay, so both are correct from linguistic perspective, but they have different. Look now, this is the first word is the same. Look here, there is renard, this is the fox, this is fast. Okay, so there are different variations. And this translation is not very good from French perspective. Okay, from language perspective is not very correct. In principle, this word should be before here, like this one is correct. Okay, so here, this blue score, it gives some information about maybe the word ordering. Also, we have the same word here, the same word here, the same word. No, this word is missing. It's not available. This is why we don't have, for example, if we take 4 gram or 3 gram, we don't have the sequence. We don't have, for example, 4-word sequence in both sentences. Look now, here I have this one and this one do not match. So even the bigram has an issue in this particular use case. This is why we have the blue score as small. So the last example, we have also an exact match, which has resulted to a blue score equal to 1. Now you can look at the code. I provide you all the code. I really invite you to dig deeper into this. You know, it's good to have some hands-on activities. I prepared this mainly for you to save time into looking for existing codes and so on. Let me just, so here we are using NLTK, which is a popular NLP library with blue score function already available, and we use the Hugging Face pipeline to download the model, and we create a translator, a French translator here. Okay, you can change the translator to German if you want. You can go maybe to Hugging Face checking if there is an Arabic version for the translation. You can try different ones. And here these are the examples. So we're going to make batch inference by creating a list of initial text and reference. So this is the reference. This is the expected translation of everyone. And you can as many as you want. And this is the total blue score. And for everyone, we're going to call the translator. And we're going to take the translation. And based on this, we calculate the blue score between the reference tokens and the translation tokens. Look now, we're going to use a tokenizer, and this tokenizer must be the same, the one that have used to, we're not going to make word by word. So the tokenization is going to decide how to divide these sentences into tokens, and then the blue score will be measured with respect to the token organization, both in the reference tokens and the translation tokens. And finally, it's going to show the statistics. This is for the first example. So the second example is about, I have model architecture here. And model architecture, let me run it through, we have a Jupyter notebook. You can run it as a Python script, or you can also run it as a Jupyter notebook. And this is a very, very nice example because it allows you to understand the translation model architectures. Let me just quickly browse this one. So from transformer, we're going to import different translator models. There is the Marian-MT model and the T5 translator model for conditional generation. So of course, these are just some instructions to load these models. And we're going to load the Helsinki translator from English to German. And let me just go here, show you more details. So in this notebook, you can see the number of trainable parameters. So these are now small models, 74 million parameters, you know. It's like a piece of cake now for current computing power. But of course, 10 years ago, that was considered as very big models. If you look at DenseNet, you know, when we talk about very deep models, we talk about 128 million parameters, 200 million parameters, which are considered like now models that can be even run on mobile phones. So this is the translation process, and it shows you through all the different details, how you tokenize. Look, this is now the input text, and these are the tokenized inputs. Look, we're going to have a vocabulary, same thing that you have learned in transformers. They're going to be transformed into token IDs, and these are the real tokens. So we have machine translation is transforming natural. This is a space. The underscore is the space before every word. Okay, this is the end of the sentence, and this is the dot. And let's look at also the attention mechanism. This is a function that shows the attention, the self-attention scores. And this is actually one of the, it's a nice plot. So how do you interpret this plot? Now, if I give you this plot and tell you, give me the interpretation of this plot. Yeah. Huh? Yes. So these are self-attention scores that goes between, look, the dark, they are low attention scores, and the yellow is a high attention score. Okay, so now machine with machine is actually, now this attention score, it's the word, it's the attention between every two words within this particular context. So here, for example, machine and translation, if we look at machine and translation here, 016, which is considered here. So this is the relation between machine and translation within this particular context. Now, if you make an attention score of machine and translation in a different context, you will have a different type of relationship, either stronger or weaker, of course, and this is based on what they have learned from the whole corpus. Okay, so this is how it is interpreted. So we can see natural, and natural was the highest self-attention score. You know, I cannot say why, because it depends on the different patterns that were learned during the training, and depends on the corpus also that was used during the training that allows to do so. And this is also another one for T5 model. So I will give you, I sent you already these codes. I want just to spend, maybe if you allow to spend a few minutes, introduce you to how to write papers. Last time